Okay, thanks a lot, Marcelo. It's a pleasure to be here in Campinas again. I was here many times teaching on agent-based model, and it's very nice to be here again to catch up and to talk about this new research. And thanks, Marcelo, for organizing this workshop with a lot of very interesting presentation. So I'm sorry I changed the title because I thought it's nice to put the conclusion of my paper already in the title. So you can really see what I'm going to talking about. And the starting point is something that I guess we are, at least here, everybody agree on, that we are in a sort of climate emergency, as was shown by the last IPCC report. Why? Because not only emissions are increasing, but also the temperature has started increasing since the 60s. And we are in a way in which every year is hotter than the previous one. Well, this year was just a little bit less than the previous year, but this is a pattern that is going on. And we are entering in a kind of uncharted territory. Here I just put some plot, and you can see if it could measure, for instance, the Antarctic sea ice extent, or the temperature of North Atlantic, and so on, or even the area burned in Canada. It's very peculiar what is going on, for instance, in 2023 from the previous year. And also we are facing increasing economic costs. So in this paper in PNAs, what we were showing was that the cost of extreme events is increasing very fast. Okay, and there is a widespread acknowledgement that market forces are not sufficient to stop this process of climate change. So we need more than market forces. Yeah. Yeah. Sorry. Okay, good. But I didn't copy. And the challenge is tall, because you know that if you want to comply with what the PCC is suggesting, we should stay below 2 degrees, 1.5 degrees, and this implies that we need to go for negative emission. And the challenge is even higher or even taller from the macroeconomic point of view, because if you take the standard computable general equilibrium integrated assessment model, like the model for which Nordhaus won the Nobel Prize, you can see that the optimal policy suggested by Nordhaus is to stay around 3 degrees, so far away from what the scientific community is suggesting. So there is this kind of problem between, on the one hand, what the world scientific community is saying, and on the other hand, what neoclassical economists are suggesting with their model that are based on equilibrium, as Basilio was discussing before. So I don't know you, but me, I will focus more, I will trust more the scientific community than Nordhaus and neoclassical economists, even if they won the Nobel Prize. Okay? Why is that so? Well, because the standard neoclassical model are not well suited to deal with climate change and complex dynamics. So we discussed in a paper that we should try to get papers that are try to embed these many features which are important for studying the macroeconomic dynamics in climate change, like innovation, structural change, lock-in, distributional problems, and night and uncertainty, tipping point, and so on. And in particular, if you focus on this approach, you are always in a situation where you have a trade-off between economic growth and decarbonization of the economic system. But actually, we argue that in principle that if you move to complexity approach, a complexity model, you can reply to the point, you can provide evidence of an important point that was made by Stern and Stiglitz in their paper, that the only possible way of growth in the long run is through green growth. So that's why we developed the DSK model, which is, I guess, the first integrated assessment model for studying the climate and macro dynamic. And I will try to show you in this minutes what this model can do. In particular, using the macroeconomic jargon, this is a model where you naturally have negative hysteresis, that is, climate shock has pervasive effect, but you can also assess the good impact of decarbonization policy. In particular, you can have positive hysteresis. So let me go on to the model. I don't have time to deal with the with the result. Let me go to the model. So the model is the simplest possible model that you can think about if you deal with climate change and macroeconomic dynamics. So similar to what also Marcelo was presenting, we have a consumption goods sector, we have a capital goods sector. The difference is that we also have power plants that produce energy that is used by the consumption goods firms and the capital goods firms. Of course, the activity of power plant, capital goods firm, and consumption goods firm release greenhouse gases into the atmosphere. These greenhouse gases affect the climate, affect the temperature, and this implies that there will be climate impact that hit the firm. Then you have a quite basic structure in terms of government, banks, household, and so on. So we don't have too much time to enter into the details, just to give you the idea that the model is called Schumpeter meeting Keynes for a very basic reason, in the sense that you have a Schumpeterian part where there is innovation, in the sense that there are new capital goods firms that are discovered by, new machines that are discovered by capital goods firms. And these new machines are characterized by different labor productivity, energy efficiency, emission intensity, and innovation occur along all these dimensions. This firm invests in R&D and they discover new stuff. And the Keynesian part is there. Why? Because the consumption goods firms invest. So here they invest in a Keynesian way, so with some sort of animal spirit. So this creates some sort of business cycle, and at the same time they replace the old machine with the new one. So this is a mechanism also for technological diffusion across the sector. Then we have an energy market where you have a firm that own many energy plants. Here we have two types of energy plant. We have the dirty and the green energy plant. We made extreme assumption that if you go for green, so renewable energy, the unit cost of production is basically zero because you don't pay for the sun. But you need to pay if you want to expand your production capacity. On the contrary, if you're using a brown plant, so think about natural gas plant, you have to pay for the gas. So you have a unit cost of production, but we make the extreme assumption that all the plants are already there and you don't need to expand the capacity. Also, this sector does R&D, so they invest a percentage of the sales in R&D, so you can have innovation in the green sector, which reduce the cost of green plant, and you can also have innovation in the brown sector, which increase the thermal efficiency of dirty plants or reduce their emissions. So you can think about carbon capture and storage technology, even if we didn't explicitly model into the model. We have a banking sector that basically provide credit to the consumption goods firm, and of course, if this consumption goods firm don't pay back their credit, this is losses for the bank, and you can also have banking crisis. And we have a climate model where the emission affect the temperature, and according to the temperature, you have microeconomic shocks that hit some variable at the firm level. So typically the shocks reduce one of the variable, and the damages that we are considering typically hit labor productivity, energy efficiency, the capital stock of the firm. You might think about all the possible natural disasters that leads to this result. Okay? So let me go to the empirical validation of this model, because typically you want to see whether an agent-based model reproduces some reality, otherwise it's totally useless. This is typically one time series that this model is generating in terms of output and emission. So this is just one simulation. And this is what happens when you have a Monte Carlo analysis. So keep in mind that here there are no climate damages. So we are in a world like Trump, that even if there is climate change, temperature goes up, there are no damages. And you can see that, there are different variations along the Monte Carlo simulation in terms of temperature. Why? Because there is technological change taking place. And you can see that the temperature, as time goes by, is increasing over time, and this I plot the Monte Carlo distribution. Of course, when you do Monte Carlo, you can compute a lot of statistics, so not only macroeconomic statistics like output growth, unemployment, and so on, but as this is an integrated assessment model, this model can give you as an output also the temperature, the emission, the share of the green sector vis-a-vis the dirty one, and so on and so on and so on. So then the other thing that we did was, okay, what are the possible stylized facts this model can reproduce? So here is a list of the macro and of the microeconomic stylized fact. And I mean, when you deal with complexity, a good thing is that typically agent-based model can reproduce also the microeconomic stylized fact. This you cannot get with standard general equilibrium or DSK model, so I think is a positive feature of the model. And I can start talking about more the different impact of climate change into the economic system. So just to give you an idea, we consider some types of shocks that hit the firm at the microeconomic level. And we get this result, in particular if you play with productivity shocks and energy efficiency shock. That is, you can see immediately that shocks that reduce the productivity of the firm are very bad for the macroeconomic performance in terms of macroeconomic growth, but also in the short term in terms of unemployment. You can see on the contrary that the energy efficiency shocks are not so disruptive in terms of macroeconomic performance, but keep in mind that they're going to be bad in another dimension in a very few minutes. But just to let you know that there is heterogeneity in the impact of climate shock that you can assess with an agent-based model. Then in this model you have what is called tipping point that people working with climate change are familiar with, in the sense that if you divide the Monte Carlo the simulation in 25 years period, you can see that in the first 25 years the cost of climate change are not so high, so you might think that everything is fine, as Trump is thinking, but then the costs are becoming more and more catastrophic. How you can see it? Well, you have the growth rate distribution in the fourth period if there are no climate shocks, and this is what happens when there are climate shocks. You can see a distribution move to the left quite a lot, and it's becoming fatter over time. Another way of looking at this is you plot some statistic like output growth or unemployment for different shocks, labor productivity, energy efficiency, and both. And you can see that in the very beginning, the shock and the cost in terms of output growth or unemployment are not so high, but then they rapidly goes up. And this typically nonlinear effect you don't have in standard computable general equilibrium model. Another thing that we did was okay, what happened with the interaction between climate and the finance sector? And typically we find that finance is not helping to absorb the cost of climate change, but is amplifying. Why? Because typically when there is the finance sector, the firms go bankrupt. As they go bankrupt, this creates big losses for the banks, and this can trigger a banking crisis. And when you have a banking crisis, this increases the number of bailouts that the government needs to do, and this increases the bailout cost. Okay? So here, just to show you that in the model you can switch off and switch on the financial sector, the banking sector, and when there is the banking sector, the cost of climate change are bigger. Okay, now let's move to a second thing that you can explore with the model, that is the probability of transition, path dependency, and lock-in. And again, if there are no shocks for the moment, you can see that the model typically, without any types of policy, most of the time enter in some sort of carbon-intensive lock-in. Only in very few cases the model is able, without policy, to go for the dynamics. And the other information that would important to stress is that the beginning, the first 25 years are very important for determining where the system goes. So there is a lot of path dependency into this model. Well, when you have climate shocks, the situation is even worse. And you can see in particular here that the labor productivity shock does not really impact too much on the probability of the transition. On the contrary, the energy efficiency shocks basically kills any possibility of the transition. Why is that so? Well, because if you have a labor productivity shock, this depresses the economy, so there is less energy demand. On the contrary, when you have an energy efficiency shock, you need more energy, and as you need more energy, it's more likely that you use fossil fuel, and the fossil fuel plant receive a lot of revenue to do R&D and so to lock the system into this fossil fuel scenario. Then we, given this result and the fact that the model basically goes in a catastrophic world, a catastrophic scenario, what we did in the last paper that we published in Nature Sustainability was, okay, is there a possibility, can we use some policy to stay below 2 degrees, so to please the scientific community, a United Nations, but at the same time to have a smooth transition, that is to preserve economic growth, okay? And we play with different type of policy. So on the one hand, we play with the fetish of any neoclassical economy, that is carbon taxes, because, you know, they always had this fixation of mechanisms that affect the price system. We have different time that is kind of small carbon taxes, that you have the transition, but you don't stay below 2 degrees. Higher carbon taxes. We play with what Nordhaus would like to see, that is an increasing tax that increase over time, as it does in the DICE model. We consider rebate, that is the money that you get with the taxes you give back to household and the firm. Then we do the opposite, so more in line of what, in a way, Marcelo was discussing before, that is we do industrial policy. And industrial policy that we do for the moment, because I mean this is an ongoing work, is subsidy for green R&D, and you also give subsidy to green energy plant construction, so to build a renewable power plant. And the other level of industrial policy that we use is the opposite of the neoclassical system, because we use command and control policy. That is policy that instead of affecting prices, they affect the quantity. So by law, for instance, you can have mandatory electrification of production in 20 years, or the ban of construction of brown plant between 20 years. Yeah, please. This model, as it is simplified, we have power sector, capital goods sector, and consumption goods sector. So we play with the sector that we have. But in principle, of course, if you have a more detailed model where, you know, you have buildings, construction sector, or when you have transportation, you could play with a wide array of policy. That's why the model is seen. With this, what you might have in mind, we catch a little bit, because the capital goods are defined not only in terms of the emission that they release, but also in terms of the fact that they use electricity and fossil fuel. So in principle, you could have over time capital goods that use less and less fuel and more electricity. So it's a very rough way to capture the fact that maybe a firm starts using electric trucks instead of electric gasoline trucks, okay, but in a very rough way. Okay, now let me give you the result. I don't know how much time do I have, Marcelo? Just oh, okay, so I have sufficient time. So the first result I want to show you is that carbon tax don't work. So all the economists talk about carbon tax, but this carbon tax don't work for two reasons. First, if the carbon tax are not sufficiently big, they don't harm the economic system, but you cannot stay below 2 degrees. On the contrary, if you want to impose very tough carbon tax, you can stay below 2 degrees, but the problem is that you cause an economic crisis in the short term in terms of unemployment and bankruptcy of the firm. So and of course all the Nordhaus schemes, they don't work. So if you focus only on the carbon tax, you have a persistent trade-off between decarbonization and economic growth. Okay, so that's what we have. So just to give you some picture to what you can do with this model. So you can use some variable like temperature change, the electrification of the system, the green electricity, and unemployment. And you can see that when you stay below 2 degrees, basically you have a big crisis in the short term. While on the contrary, where you are not able to stay below 2 degrees, you don't have a crisis in the short term, but you will have a crisis in the long run. Why? Because the climate shocks will be bigger and bigger. Okay? Then we try with all our industrial policy, and we find that this command and control policy are very effective in stimulating a rapid transition in both the energy sector and the manufacturing sector. Why? Because we have what is called nowadays direct technological change. I mean, using the word of Acemoglu, but actually is what has been there for decades in evolutionary tradition, from Nelson and Winter, Dosi, and so on. That is, by putting the regulation, you are steering the innovation of the firms towards the green section, okay? The green sector. Of course, if you add industrial policy, is even better. Why? Because not only there is the stick of the regulation, but there is the carrot of this subsidy that promote the building of green plants and the promote green innovation. If you go for both, you have a very nice result where you can stay below 2 degrees without having basically a crisis. Just to give an idea, indeed, the unemployment, is not so high. Sorry for the color, but we need to deal both with what the review asked us in terms of color, and there is also a German co-author, so it's difficult to pair color when you have a German co-author. Okay, apart from the joke. Another result that we got is, okay, this policy works, but they are expensive, they are costly. So imagine again that you don't want to increase the deficit. I don't know Brazil, but in Europe there are many countries that don't want to do deficit and whatever. And so our idea is, okay, let's put a carbon tax, but in this case the carbon tax is not the main device, the main instrument to decarbonize the whole economic system. You just want to have a small carbon tax to pay for the industrial policy, and these things more or less work. So you can have, with an agent-based model, this type of result where you try all the possible policy and combination of policy, and you can assess the policy along different dimensions, which involve the peak warning, how they penetrate in the system, the unemployment rate, the bankruptcy rate, and policy cost. And you can see that the real trade-off that you have is basically, actually the best policy that you have is the policy where more or less you have the industrial policy plus a small carbon tax. If you don't want to have the carbon tax, okay, you have to accept a deficit, which nonetheless is not such a big deficit, not that your public debt over GDP goes on an explosive path. It's still staying in a good path, but I mean, if you are deficit Taliban, you can introduce this carbon tax. Okay? I skip this because I don't have time. I just want to say, to show you what we do also that can do in this paper. The other thing that we do is that you can decompose the impact of this climate policy in the short run, in the medium run, and in the long run. So basically, when you go for the long run, you can assess what happened at the end of the simulation, if you go for carbon taxes or if you go for industrial policy. And of course, you can see that here the industrial policy dominate the other one. In the medium run, what you can assume is the idea that we have is that we start with, we consider in the simulation the very beginning where the green energy is below 10%, the transition phase where the green energy is growing, and the last phase when the green energy is high. And also here, so to speak, we use this type of experiment to show that this policy works very well also in the medium run. And the last things, we consider also the policy in the short run. So here the idea is, well, imagine the economy is in a recession. Is it better during a recession to go for carbon tax or to go for industrial policy and so on? And in a way, this plot, I mean, I know it's a little bit dense, there is a lot of stuff, show you that this type of climate policy are also very good in the short term. So if you are in a recession, by going for this green industrial policy, not only you go out of the recession thanks to the investment, but at the same time you are decarbonizing the economic system. Okay? I skip this and just let me, just give you the final discussion of this paper. So we show with this model that the climate costs, if you don't do anything, are going to be catastrophic because they are tipping point. And we find that if you have command and control and green industrial policy, you can break this trade-off between growth and decarbonization. Why? Because in the short run, you have this Keynesian effect of investment. In the medium run, you have Schumpeterian dynamic in the sense of the development of new green technology, and in the long run you avoid the catastrophic cost of climate change. So in a way we find that if you go for Keynesian and Schumpeterian policy, you can find that the result, there is no trade-off, but the result are complementary. You can catch two birds with a stone, in the sense that you can trigger positive hysteresis, preventing negative hysteresis, and you can reply to the point of Stern and Stiglitz that you can have in the long run green growth. Okay, so let me finish with this, which I always like. I take it from Banksy in London. So first, your point. In this simulation, there is no inequality, but we have started expanding the model to account for inequality. So you have in the agent-based model some sort of social classes like manager, capitalistic, and worker. And we publish a paper in the journal Economic Behavior Organization talking about that. Of course, it's just the beginning, because in principle, I mean, you should consider the whole income distribution, because there is this evidence that the top 10% are those responsible for climate change, but the bottom 50% are going to pay it half. Kind of to your point, Abin, well, we didn't go for popularity, also because these policies are never popular. Nobody's doing industrial policy. So we chose according to what we thought was feasible and interesting. On the one hand, we wanted to have regulation because it's something that is typically overlooked, at least in the mainstream regulation. So we thought about a couple of regulations that was compatible with this model. And we thought about industrial policy that were too much market-based, but was easy to implement. What we are doing now is to try also to have some sort of mission-oriented industrial policy, because we have another paper, Without Climate Change, with Mariana Mazzucato, where we try some sort of entrepreneurial state, and this would work. These are nonetheless demand policy. Even the entrepreneurial state are not demand policy, because that's your point with the too much supply side. I'm a little bit skeptical that you can decarbonize the economic system with demand policy. So you need to move more on the supply side, but at the same time via some sort of, if you want, Keynesian multiplier or the other, you can keep the wage high and have this effect on the demand. I don't know if I got the last question. Point, if I understand well, is how you finance this, because the cost can be higher than what I was discussing, right? Or, well, the literature tells you that the cost, if I'm not wrong, are around 1-2% of GDP. So actually, even now, even in this economic system, it wouldn't be so much expensive to finance the transition. I don't know Brazil, but consider that many countries in Europe are moving from 2.5% of the GDP allocated to the defense, that is actually is war, towards 5%. So if they would move to decarbonization, that would basically solve the problem. And this model, we get some results that are in line with that. So you can do 1-2% of extra deficit if you don't put the small carbon tax, and the small carbon tax solve the problem. Of course, you don't have to necessarily, I don't believe exactly in this result, but it's more like qualitative scenario to show you that this is, so to speak, possible.
So, Nicholas, I'm sorry that we were ready to watch this for 2 weeks ago, but we not. So I'm a full stop researcher here at actually, it's very nice to present this again for you, because actually the first time that I heard about the book and myself some years ago, for some years here I am this work. And so basically, the title of the work is Macroeconomic Impacts of Climate Change on the Brazilian economy through the and the name of the paper is already says, my objective research in the book is to analyze how the macroeconomic impacts due to climate change on the Brazilian economy, with the main focus on this paper specific on the shock organization. And why the focus on the electricity sector? Well, basically because we are quite proud of our nature, because it's one of the most clean
energy in the world. Our energy is highly concentrated in Brazil in the hydropower, using hydropower. However, this has become and is becoming a vulnerability for our country, as we'll show in one moment. This real motivations for the research. I also had a personal interest in doing this research because basically I did my PhD studying inflation and with using an ABM model, but we have the problem, or model that I developed was quite hard to have high inflation as we observed in 2021, 2, 3, without a strong decrease in unemployment. So in these models, normally you have the curve working on, like Lillian's model, like the model Lillian described. And here I wanted, okay, but I was interested to understand cost shocks in an ABM. So, yes. Okay. So, the motivation then, okay, also what is interesting is that with this paper I'm trying to discuss a bit, okay, with some shocks that we had recently. So we have the COVID pandemic, we had the Ukrainian conflict, the trade war, now we have the Iranian war. And all of this creates all the time a lot of commodity price volatility. And this has direct effects over the Brazilian economy. We are not separated from the rest of the world. But in our case specifically, Brazil is really vulnerable to one specific supply shock that is due to changes in the climate, specifically in changes in the rain patterns. So there is a large literature here in Brazil, not from economists, but from climatologists or geographers, saying that probably in the next years or decades, probably the rain pattern in Brazil will change due to the climate change, and also due to deforestation in the Amazon, as I will discuss in 1 second. And because of these changes, it is expected that maybe until 2025, in the next 25 years, it is expected that the production of energy coming from the hydroelectric power stations will be decreased around 5 to 15%. This is a huge problem for us since, okay, we are saying that in the next decades, probably we will have a decrease in the energy production from the source that in 2009 was 70% of all the energy sources that we had in Brazil. So Brazil, about 70% of our energy production comes directly from hydroelectric power plants. Although this is decreased over time, it is still highly concentrated, even still at nowadays. So just to show what I'm trying to discuss here, okay, what is the whole mechanism that we have to explain how climate change will decrease the rain patterns in Brazil and how this will affect our economy economically through this mechanism of energy effect. Well, here we have this picture that comes from geography textbooks of high schools in Brazil, basically showing that our rain patterns, we have the oceanic winds coming from the north. They come through the north to the Amazon rainforest, and because we have this forest, we have sufficient conditions to have humidity, and all this forest keeps this humidity strong. And with the winds, because here we have the Andes mountains, then we have all this rain that is generated to the southeast. Now, what's the big question is that these sources of forest are necessary basically to keep this amount of rain in the clouds to fluctuate, basically to travel to our rivers where are located our hydroelectric power plants. If we don't have this forest area, basically we don't have enough conditions basically to transport through the air all these clouds to our rivers where we have the reservoirs that are used to generate electricity. And that's the issue because the majority of the hydroelectric power stations in Brazil are located in the southeast, or maybe in Mato Grosso, where still a concentrated amount of hydroelectrics. So basically what I'm saying is that because of deforestation, due to mankind, due to man processes, but also due to climate change, it is expected that this amount of rain that comes from the north using this path from the Amazon will decrease, and probably we have a decrease in the inflow of water that supplies the water of the reservoirs in the southeast that basically generates 70% of the energy in Brazil. And not only this, it is something that we will expect, but Brazil is already have faced two important climate shocks due to decreases in the reservoir of water in the last 15 years. So I don't know if who is here from São Paulo, but in São Paulo we had a strong decrease, a strong drought here in São Paulo in 2014. We can see this in data. So basically, this blue line is the average storage capacity of our reservoirs. We had this strong drop here in 2015. And then basically we had this price shock. The red line is the increase of the weekly average variable cost of the energy prices. And then again, we had another price shock in 2020 and 21 together with COVID. We did not discuss much of this, I think, because COVID was happening. We had another more important things to discuss. But here we had another huge price shock at the same time. And here with this scatter plot, we can see, okay, basically when the reservoir capacities are below 50% more or less, we start to see a high increase in the volatility of the variable cost of energy production, and also an increase in this variable production of energy over time. Then basically what I try to do is to get all these motivations and data to try to put all this in an agent-based model where I have the objective to have a model that more or less is able, or the more better that I can, is a model that replicates the structure, the Brazilian structure. And why? Basically, I wanted to test, okay, if we make a shock in this model that has a structure closes or resembles the better that I can, the Brazilian economy, how this shock will propagate in this economy with the Brazilian specificities. So in this model, I have 6 types of agents. I have the non-financial firms, where basically almost all the actions happens, as I will show in the next slide. I have an energy sector, where I have the energy producers and a monopolist energy distributor. I have a representative household sector, so it is an aggregate sector. I have a government sector, a central bank that is simply modeled using a Taylor rule. And I have a banking sector that is really simplified. It basically accommodates all the credits demand comes from the firms. It is a multi-scale sectoral model. So here I have 12 sectors following the Brazilian national accounts. Here I'm using all this structure for the national accounts and parameters really to use as an anchor in the model. So I try to calibrate the model and the parameters to be able to reproduce the better that I can all these Brazilian national accounts that come from IBGE. And since the most, at the first level disaggregated from the most aggregated level, is with 12 sectors. So I'm using here as well 12 sectors. The initial conditions reflect the structure of the Brazilian economy, especially of 2019, where I have mostly of the data disposable until 2019. And just as a simplification, a strong one, is that in my model, for now, the economy is closed. In terms of non-financial firms, the model is really normal. So basically what happens here is what you see in most of the IAMs model. So firms form expectations of demand using adaptive expectations. They produce the final goods from the consumers. They also buy intermediate goods, so firms can buy goods from each other. Here's where I enter the energy use. Firms demand and pay for labor from this aggregate representative household. They invest in capital stock. They invest in R&D, so to improve quality. So here I'm assuming that firms have different goods of different quality. So this is basically the other source of shocks that I have in the model, basically what's explaining the volatility in the model, and make price decisions. All of this is super usual, and you will see in the majority of the IBM models. What's really I'm trying here to contribute to the literature is to model in a really simplified way compared to the paper that you will see in one sector after me, But you see, it's a paper where I try to explain, okay, if we have a shock in this energy sector, what happens in the macroeconomic, at the macroeconomic level? So here I'm trying to replicate at the energy level. I try to replicate some key idiosyncrasies or specificities that we have for the Brazilian economy in terms of technology, market structure, and regulation that are really specific for Brazil, quite different from the US or Europe, for example. And then basically, in my model, I have three types of agents or producers of energies. Basically, we have firms that produce energy using renewable sources of energy, wind and solar energy, hydroelectrics, and thermal energy. And to calibrate all of this is quite interesting because we have actually a lot of data for the energy sector in Brazil, especially coming from the energy planning company, Empresa de Pesquisas Energéticas, and also we have from the national organized ONS, operator of the national system. So Operador do Sistema Nacional, they also have many data disposable to us. And with all of these data, we have a good idea of the cost structure of these different power plants, and we can calibrate the model. Oh, and also, quite important, this is why it makes sense to use an ABM to explain and to use this, because here we have a strong strong heterogeneity in this sector, so we have really different technologies here competing among each other. It's not just differences in technologies. Here we have really differences in the production functions, and this really is why it's justified why we should use, or to use an ABM model is a good instrument to analyze this type of question. So, everybody knows this, but what are the main differences among these three technologies? In terms of renewables, is that they have the median generation cost, but they are highly volatile, so they are extremely weather dependent. If you think in terms of wind, it depends on the wind to generate energy, or the solar energy. Hydroelectric power plants, they are really very low. The cost of generating energy with hydroelectric is really low. However, the output is really volatile and dependent of the rainfall conditions. And probably have in Brazil a limited, we have basically got the limits where we can, in terms of production energy coming from the hydroelectric. So in other words, the potential that we have we don't have more potential to increase the system anymore. Basically, we are producing all the energy that we can pretty much coming from hydroelectric power plants. And in terms of thermal, well, they are really reliable. They are dispatchable 24 hours, no matter what's happening in terms of weather events. However, they are really costly. The cost to generate energy using thermal electricity is really high. That's the main disadvantage of this energy. So just in terms of energy market regulation, I try to replicate this, of course, in a model, in a simplistic way, how we regulate the energy market in Brazil. Basically, we have the energy research company that dictates how much each energy power plant can produce at the limits in terms of capacity. But then in Brazil, the National Electric System Operator, ONS, is basically all the time imposing limits of how much each of so it's basically a command and control, pretty much, system, where this operator, this regulator, dictates how much each one of the power plants can produce at each time. So basically, this operator is coordinating all the system in terms of production, but it's not setting prices. Basically, let's say, okay, Itaipu, you can produce X. I know that your limit is 2X, but now, given the conditions of the system overall in the country, you can only produce half, for example, of what you can. This has an effect because I'm assuming this model that all these firms, given how much they can supply, they compete among themselves in an auction. So we have here an increasing auction, an English auction, where basically we have a demand for energy coming from the system, and through this auction mechanism, we have these power plants distributors competing, generators competing among them to sell this energy to this monopoly centralized distributor. And basically we have this, this is our supply curve of energy in Brazil. This is generated with the model, but it's nice, it's interesting because this result is really direct result from data that comes from the Brazilian structure. So we have here that to produce until 80,000 million megawatts, this is quite cheap to produce energy in Brazil, basically because we are using our hydroelectric potential, and this ascending curve is basically going to start to use here in Brazil the thermoelectric power plants. So we have that, imagine that we have a constraint in how much we can produce here at this space. So we have a constraint the use of hydroelectric power plants. Then basically we need to start to use the thermoelectrics. They basically have an increase in our cost of megawatts hour in reais. So this is the source of shocks here that we have in our model. So just to skip the results. So then this is an ongoing work. So comments or suggestions here are super welcome. But these are the three scenarios that I have so far, the three experiments that I have made so far. So here I have a benchmark where basically I'm assuming that the rainfall follows the historical patterns that we saw until 2010, more or less, with no decrease over time. Then we have experiment 1, where we have a temporary decrease in 40% of the inflows of rainfall in the reservoirs of our hydroelectric power plants, which is basically what happened in 2019. And this happens for 4 periods, which are equivalent of 1 year. So basically, each period is 1 quarter of a year. And then we have experiment 2, where we have the permanent decrease in 40% of the reduction in rainfall from period 4 onwards. So this is basically our worst case scenario. We're assuming that from next year we have a permanent decrease in the rainfall until the end of the days, basically. But this is the worst case scenario. So in the worst case scenario, what would happen? And this is the result. So here in blue line, I have the benchmark, the baseline scenario. In orange, I have the experiment one. So I have this transient shock, this transitory shock. And here in green, we have this permanent effect of decrease over time in the inflows of water in our water storage. So basically, as we would expect normally, okay, so basically we are here departing from this benchmarking of a use of 65% of the water storage. Then here we have this strong drop during 1 year of the water storage. Then after this decrease of inflow of water, this basically due to the action of our regulator here, basically because it decreases how much the hydropower plants can sell, we have the return, the comeback of the water storage to the normal conditions. And then here on green, we have this permanent decrease in the water storage from 65% to 58, more or less. Now the big question is, okay, what are all the other effects that comes or appears or emerges from the model from this? Well, since we have a decrease in the water reservoirs, as we would expect, basically we have a decrease in the hydropower sold, that is sold to the hydroelectric power plants. We have a comeback in the experiment 1. So, okay, if you have a normalization of the supply conditions in terms of inflow of water, we have a normalization how much you can sell in terms of energy coming from the hydroelectric power plants. But here in green, we have a permanent decrease in the energy that is generated through the hydroelectric power plants. Now, in terms of tariffs, so in terms of shock, and this is, I think, that is an interesting result, that since the model is all more or less calibrated to Brazil, we have here a result that reflects the Brazilian structure. And since I'm using here data from 2019, I'm trying to compare my results to what actually happened in 2021 in Brazil to see if my results more or less resemble what happened. And here, in terms of transitory effects, then basically what we have is pretty much the price, the final energy tariff, pretty much doubled through this period. And of course, basically, in the scenario experiment 1, we have a comeback of the results. So with the normalization of the supplies, we have this result, the energy supply comeback. But of course, in the case of a permanent decrease in the use of energy coming from hydroelectric power plants, we have this permanent increase of the tariffs for the consumers. And not only this permanent increase, but we have a strong increase the volatility of the price over time. Why? How can we explain this? Well, basically, because imagine that the Brazilian economy in this scenario is operating at this level. So basically, if you move just a little bit in terms of your GDP or production, the price will change considerably up or down. That's why I can explain the volatility in the price. Well, now in terms of inflation, then I expected that I would see a much higher volatility in inflation. That's not what I observed in this model. So, okay, we have the transitory effect here and a permanent effect, but we did not observe, we have an increase in the volatility of inflation, but in terms of the level of inflation, I did not observe a strong increase, permanent increase in the inflation in this model. Doesn't matter in experiment 1 or 2, but on the other hand, what is interesting is that we have a shock here of only 4 periods, and after 10 periods, so 10 years, we still observe effects in terms of volatility inflation. So we have the cycle of inflation due to a shock that only happened during 4 periods. So it's quite a permanent effect. Or the decrease of inflation is quite slow to have the convergence to this baseline, let's say. In terms of GDP, we also observe this pattern close to what we see in inflation. So we have an increase in the volatility as well in both scenarios. We have a more stronger effect when in the permanent scenario. So we have here a decrease in GDP. But in both scenarios, we have the cycle. In both cases, after 10 years, I do not observe this effect of shock decrease over time or convergence to this baseline level that I would expect a scenario with no shock. Energy demand, unemployment. So just to go to the results, that is interesting that, okay, but one key variable of the model that reflects macroeconomic variables is interesting that we have a permanent effect, is that in terms of real wage. So basically, after this permanent change in the conditions of production of energy in Brazil, assuming that structure of 2019, we observe a permanent decrease in the average real wage of the economy from here is 3.400 reais to 3,000 reais. And how you explain this? Well, basically, because through the auction mechanism, you are having to sell energy more costly, and all this difference in prices basically is an increasing of profit. So basically, the distributors of energy, the generators of the energy, they are having more profits, basically because in the auction the prices goes up. So, and I don't have in the model any mechanism that automatically or somehow distribute this increasing profits in the energy sector to our workers in the model. So basically what we have here is a decrease in the average real wage of the workers or in the model, or a concentration of income in the model. So this is the permanent effects that I have. So then the key results that I have so far in terms of, okay, after the scenario of the shock that tried to replicate what happened in Brazil 2020 and 21, we have an increase in 150% of energy prices, a real wage decline of 13%, a really slow convergence, if we have a convergence of the system to the steady state, in the case of the transitory shock, and a strong increase in economic volatility in both scenarios of 3 times basically. So these results so far, so I'm working still on, many results can change depending on the work that comes, the calibration, etc. But so far we are demonstrating that Brazil is really vulnerable to economic shocks, and these shocks, if they happen, they can have quite sustained effects in the economy in terms of, especially of volatility. We have a persistent increase in the volatility due to the shocks, and especially the variable that will most changes with this are permanent changes in real wages. And for future developments, of course, we can do some fiscal policies to see how fiscal policy can smooth the cycle. of course, do better empirical calibration, validation, and do scenarios with changes in the energy mix. And that's it. Thank you. So, Paula and Roberta, I think that your model, the question is pretty much the same. And you are pretty much aligned with Andrea and Marcelo because they did exactly the same comments when I last presented. So here this is the key main strong assumption in the model where I don't have technical change. So here we have permanent technology. Basically, I have all this data from 2029, and I use this data to calibrate the model in terms of technology. And Paul, I'm assuming that the structure is constant over time. So this is, okay, I did the simulation. Basically, in my mind, I have, okay, 2020 until 2030. But over the last years, as you said, the structure of the Brazilian economy, the energy mix is changing considerably. And no, here's the weak point. That is something that I'm working on right now. Is basically, okay, what if we had a model where we have changes in the parameters of energy and we have changes in the energy structure mix? What would happen with the model in terms of results? But then this is something that I'm working on, and for sure it's something that I need to address because for now it's too simplistic. Basically, I have the structure of 2020 and assuming this constant over time. So, but great questions. Forgot your name. Rubens, yeah, so good question. So if I got your point correctly, it's basically to see, which is more or less, I think, relates to the point of Paulo. So to basically, to have policies to change the energy mix of, vou falar em português, para mudar o mix, basicamente, isso vai afetar, reduzir a volatilidade, né?
How are you? Okay, how are you? Good afternoon, guys. How are you? So I'm Marcelo, and yes. Excuse me, Marcelo. So along the time I started to talk at lower level. I don't know why. I used to speak very loudly and such and such. So I'm Marcelo. I'm presenting the result of a thesis that was done by Stephanie Ruiz, and it's I am a co-tutor on the side of José Maria. Of her, she presented it in the past January, and it's about the biomass waste market for advanced biofuel, and we applied an agent-based model to assess the supply chain of a waste biomass, market. So just to start with the motivation. So the USA produced 70 billion liters of ethanol compared to Brazil. That's half of that, 35 billion. India is the third one for ethanol. That's around 5 billion liters. And you have Europe producing 13 million of tons of biodiesel per year. Just to give you a picture of what it represents, in terms of volume, and the motivation is to increase the supply, just to increase the ethanol production. The supply of waste biomass could increase the ethanol production on about 23%, using just the waste from the sugarcane production itself. So that's the point here. That's the importance of this work in this assessment. So how did we start to this study? We started from that agricultural waste is essential for the improvement of advanced biofuels. It's based on Maducana, Setwall, Wang, Mola, Yadego, so a lot of people, Bunny, that's Brazilian one, Bartolini that made a nice work on ABM in Italy, and a lot of other references. Just to get just to model the market as this. So we started with geographic heterogeneity for the biomass supply. You know, where we have distinct waste types. We have this challenge of developing institutional arrangements. We have the challenge of the uncertainties due to the biomass availability, seasonability, quality, price, and long-term availability. And at the end, we have the challenge of reducing transaction costs and risks for the business, for all the business that it includes the suppliers and the biorefinery itself. So all of our study, it's focused on transaction costs, right? And some idea of intermediate economy from Spielberg, as Jose Maria suggested us. What is important here is when we think from the biomass, from the waste, from sugarcane production, we are thinking of that we are going to get the biomass from the traditional first generation ethanol production, which is limited itself, you know. So that imposes some limitation to the size of the market. That's why when we modeled our market, we limited the biomass production, the total amount, and we fitted a biorefinery for that amount. So what do we have here as questions? We have the problem of the seasoning, the season, the off-season ethanol production and prices and price volatility itself. We have the problem of the frequency of supply, crop type, distance, and size. That's the main factors that we tackle in this study. We decided to make to simplify the model to approach only the interface of the supply. So you have on one side the farmer, and the other side you have the refinery, and the market gives the exogenous prices to the simulation of this market. So here you have the main agents, which is the biofuel market. You have the biorefinery here, the sugarcane farmers, and what they produce, and how they get the production, and how they and where they produce for the first generation ethanol, and where they produce for the second generation ethanol, biomass for each of them. So, and we have our assumptions that we have just one market, we have just one biorefinery to start, and we have a bunch of farmers, 670, divided in 2 types and 5 distance ranges. Sorry? So, what do we have here? We have seasonality of ethanol prices. We have the biorefinery as a price taker, and it transmits the price signs to the farmers when it make the offers for the biomass price, for the biomass straw price. Okay. So we have adaptive behavior of the agent. So the biorefinery changes its markup depending on its operational level, or how much how much it needs of straw to process and produce ethanol. The farmers, they try to exfoliate the biorefinery also. They try to get the better margin as they can, and they reduce their margin when they don't do business, you know, looking for the best efficiency on their market also. So how what is the timeline that we have for the simulation? We start from the market, which announces the ethanol prices. We took a 20-year series of ethanol prices. We modeled it. We modeled the seasonal variation of the prices, simulated it, and we got this distribution at the end, along the months of the year. So the biorefinery, it takes the main decision based on its unit costs. It calculates its break-even level of production. Based on this, it calculates its price, which price it's going to offer for the farmers for its raw material, to get its raw material. Here you have the sequence of equations that defines the adjustments of the margin. And what is important here, it is we don't get stuck in it's not a net margin, it's not a profit margin, but it's bargaining margin itself. It's so it's not limited. From the side of the farmers, what we do to make the experiment, we reproduced the 5 different land structures, because the land tenure, based on some old papers that we had before, which says that if you have more equitable land distribution, you would have more efficient market, right? So we try to model different Gini index. So we started from the São Paulo state with this distribution that you have mostly 10% of the producers, they own 90% of the area. And in Brazil, you have the second level here, in which one you have 20% of the producers, they have 80% of the area. And we continued, just to make, as it's a model, let's go to the 50-50, and we went to 30, 70%, 40, 60%, and 50, 50%. That is 0.5 G, right? So the second, and here we had 134 farmers per each farm size experiment. So we multiply by 2. We have foraging collectors, foraging farmers, which they go there and they collect the straw from the ground. And you have baling farmers, which packs the straw, and they make stock of the straw, so they can get better prices for during the off-season time. Here we have 2 cost curves, that refers to different technological levels, and it varies according to the productivity level of each farmer. What is important, it is we don't simulate technical change in the model. So there is no learning process or diffusion process of technology that would improve the level of production of the suppliers. The suppliers don't change types. So our model in this way, it's very squared, because we wanted that the market to work to get results and to check out what is the business as usual for the market. We have the 5 different distance. All of the simulation is heavily based on data from the Sucre project, that is a sugarcane research for electrical production, that was based on the LNBR, Laboratório Nacional de Biocombustíveis Renováveis, and the other source of data, it was the virtual biorefinery project by Bonomi and Marcelo Cunha from Institute of Economics, right? So here it is, from the farmers you have a huge amount of equations to define the bargaining margin also, and its results and the straw price itself. So in the transaction loop, we do a pairwise matching from the biorefinery to each farmer, and it's random, a procurement strategy with no any kind of pool for the farmers to participate to the market. So everything is free, and our objective here, we were aiming to get the range of result as far as possible, as large as possible. So which results do you have here? We don't have the numbers here. I don't know why. But what we have here, there was a table. And this table says that for all the experiments we did, we have the mean performance of the biorefinery of 40% of use of its capacity. That's pretty low. Anything can be feasible at this level of operation. And the maximum level of production achieved, it was around 84 to 85%. In the model, we did 100 replications using Monte Carlo. So in the results, here we have comparison of different land structures, and there's not much different results among them. But here it is, the biomass supply, and you have the sales that the farmers they did. It was around 25%. That was the total. This is the total production of biomass, of waste biomass. Just 25% was sold to the biorefinery. So this is what was effective. 12% it was left in the field, and around 63% was lost. Was not sold. It was totally lost. So this is the picture of the results in terms of performance of the market. Something that it's interesting here, it is that you see some difference of the producers that they are balers. When you consider the volume of the straw sold to the biorefinery, the balers they sell more than the ones that they collect the straw from the ground, that it's in red. The balers that they are in green or blue, something like here. But in the number of the farmers who participates in the market, the foragers they participate in a bigger share. Why does this occur? It's just a consequence of the land distribution. It's not something that it's really attributed to the market performance itself. Here you have in the red, the participation of the foragers, that they are fitted much more with the seasoning collection of the straw, and you have the balers with a better performance when you have the off-season. It looks like to us that there is a sort, it was, it emerged, it was an emergence of the simulation. The behavior of free rider attributed to the foragers farmers, the farmers that they collect the sugarcane from the ground, because they just collect when they sell it. We applied a determinants model to explain the determinants of the results of the results. It was done in the end of the process. So all the data from the 240 months, they were packed in the end of the simulation, and we used a simple 2-bit model to explain. We started the econometric determinants model we started composing the model from the ground itself, from the production or from the ethanol price assigns, the landed tenor structure, and we go to the agronomic variables here, the straw characteristics variables here, that impurities, moistures, densities, that they are the source of the asymmetric information. And on top of this model, that it's based on the material side, we put the unit cost of straw. You know that it's the first sign that comes from the farmer itself. In the third model, we added another layer that refers to the logistic costs. And the fourth model, we added another layer of the bargaining margin to check out how the bargaining margin explain the results. And at the end, we apply the quality discounts based on impurities, moisture, and density to the final price to check out how that works and how that explains all the results that we had. So first, something that doesn't show in the when you analyze the graphics, the box plot graphics among experiments, in the econometrics, it shows that the first three land structures, that they are the most concentrated ones, they have a higher impact in the performance of the market. That's huge here, 21%, 24% of elasticity. It's a huge impact. You know, and second, the ethanol price, higher ethanol prices, they determine, you know, a lot of the results. At 187% of the results. You know, this is the most important driver of the ABM model that we produced. And third, here you have the biomass characteristics, that it's related to the specificity of the assets that are traded. And what is important here is density of the straw. You know, when you pack it it's more dense, so it makes more efficient for the market. And something that it's the unit cost for sure. It's less 3%, just 20 minutes. Yeah. And what is nice here for us, it is the bargaining process. You know, it played an important role in determining the final results of the simulation, that it decreases the market performance in 120%. That's very good. And when you apply the assets characteristics to the price, you know, it falls down. The elasticity is negative by 400 by 4 times. Right. So what do we have as a result here? We found out a structural coherence between the ABM and the econometric validation that we used. The econometric validation was applied just to check out how the variables they were behaving inside of the model. Production scale, land concentration, biomass quality, cost, and bargaining margin, they are important determinants. We have some, I just want to show you here that we imposed a very strong information asymmetry among the farmers and biorefinery, so nobody learns with nobody. Everything is closed down. And I would like to, so we have some key messages here. I'm going to skip that just to show you something that I learned in the past 15 days when I was breaking down the results. You know, I went to check out how the adaptive mechanism that we introduced to the ABM, they were producing different results. Here you have the simulation, the Monte Carlo mean and confidence interval simulation of the ethanol prices. And in this graph down here, you have those prices broken down in different operational levels of the biorefinery. Here we show that the biorefinery requires for sure a higher ethanol price to work. It's pretty distinctive of the other ones. In green, you see the prices that they are over the break-even point, but they are not enough to make the biorefinery to work. And as we made a large simulation of situations here, you have the prices that they produce a negative break-even point also. What is that? So, and going further, and checking out the results here. This graphic, it is the ethanol production level when the biorefinery is not buying any biomass. You can have some production because it bought something in the last period, so it would have some marginal production here. But this, I just made this part of the graph, this part of the analysis, just to check out what is the leftover. What is important is it is down here. Here you have the production, right, against the time, and the production level, it's broken in 3 different situations, 3 different levels of production. In blue, you have the biorefinery operating under the break-even point, and it strategically applies a reduced margin. In our model, there is a delta that is multiplied by 3%, and it tries to reduce its margin just to acquire more biomass. So that's why it has a lower level of production, but it has a lower level of production. So it was effective. And in green, you have the delta as -2. So the biorefinery is operating over the break-even point and under some frontier of efficiency that it's near to its 90% of its capacity. And in the red, you have the full operation of the biorefinery, describing, and it is when the biorefinery tries to spoliate the farmers and it tries to increase its margin of bargain. Right. That's it. So, thank you.